Hello, everyone, and welcome to the first section on indefinite integral. So, in this chapter, the ultimate goal is to compute indefinite integrals, which means finding all antiderivatives of a specific function. And the quest to get there is quite challenging, but we'll get there one step at a time. So here we go with our first definition. So if you start with f of x, small f of x, a function, we're going to say that big f of x is a primitive or an antiderivative of that function, small f of x, over an interval, typically the domain of that function, if big F prime is equal to small f for all x in that interval. So basically here the notion of primitive is just if you want to check if a function is a primitive, well, you just need to compute its derivative, and if it matches the other function, then yes, it is a primitive. So let's just do a bunch of examples, and these examples are typically right now just verification and a review of differentiation. For example, suppose that big F equal to 2x cubed. Let's show that this function is a primitive of small f, which is 6x squared. So here we go. So this is like a derivative question to some extent. So let's compute the derivative of big F. So we want to compute the derivative of 2x cubed. So we're just using the power rule. So the 3 falls on top of the 2. You get 6. The new power is the former power minus 1, which is 2. So you get 6x squared. And of course, that's the same thing as f of x. Yes, we just verified that the derivative of big F is small f. But now this primitive is not unique because, for example, if we pick big G, which is 2x cubed plus 10, so I just basically took my previous example and I added a 10 to that function, I'm creating a new function, of course, but that function is again going to be a primitive for that function. And let's just verify that together. So let's compute the derivative of big G. So let's compute the derivative of 2x cubed plus 10. The derivative of 2x cubed is again 6x squared. 6x squared, sorry. You won't see that little mistake. And the derivative of 10 is 0, which of course simplifies again to 6x squared, which is again f of x. Yes, this new function big G is also a primitive. So this should tell you right away that the notion of a primitive is not unique. You cannot say compute the primitive of a function. You can just say find a primitive of a function. Or, of course, the ultimate goal here will be to find all of them. But it's not too difficult to understand that if you have a primitive and you create a new function by adding a non-zero number to it, you're creating a new function, and that new function will be, again, a primitive. All right, so let's do another example. Let's show that big f of t, which is 2 square root of t, is a primitive of small f of t, which is 1 over root of t. So again, here, no big surprises. The goal is to compute the derivative. So let's compute the derivative of big f of t. When you have a root function, it's good to write the corresponding power. So here we want to compute the derivative of 2t to the power 1/2. Again, we're using the power rule. The 1/2 falls up front, multiplies the 2, becomes a 1. The new power is the former power minus 1. 1/2 minus 1 is minus 1/2, so you get t to the power minus 1/2, which of course simplifies to 1 over t to the 1/2, which is the same thing as square root of t, which is the same thing as small f of t. And yes, when you compute the derivative of 2 root of t, you get 1 over root of t. So that big function, big F, is indeed a primitive for small f. All right, I know you're screaming, more, this is too cool. All right, so let's verify that the function x ln of x minus x is a primitive of the function ln of x. Again here, no big surprise, you just have to compute. This is a verification question, so let's compute the derivative of big F. So let's compute the derivative of x times ln of x minus x. So for the first term, I have to use a product rule because x is multiplying ln of x. So the derivative of x is 1 times ln. I'm going to get ln of x plus the first function, which is x times derivative of ln of x, which will simplify to plus 1. The derivative of minus x is minus 1. This simplifies to ln of x, which is small f of x. Yes, sir. Okay, it's indeed a primitive. So just to make sure, to be clear here, the ln of x plus 1 was the result of the application of the product rule. All right, and as a last remark on that page, but I've already mentioned this, the notion of a primitive is not unique, because if you have one, you can construct another simply by adding a constant. All right, we can now summarize this idea with the next theorem. So if you start with a primitive, if you construct a new function, which is that primitive plus a constant, that other function is going to be again a primitive. So formally, suppose we have small f, a function, and big F, a primitive for that function small f on some interval. So big F prime is small f. Then the new function defined by big G of x is equal to big F plus C, where C is just a constant, a real value. Then this big G is going to be, again, a primitive for that function. So let's prove it. So to prove it, we just have to show that G prime is small f. So let's compute the derivative of big G. So big G is by definition or construction big F plus C. So we want to compute the derivative of big F plus a constant. The derivative of big F is f prime. The derivative of any constant is 0. Because big F is a primitive, then big F prime is small f. Small f plus 0 is just small f. That's it. That's all. Big G is a primitive for small f. Again, this is not a surprise. Okay, so because the derivative of a constant is 0, this big G of x will obviously be another function that is again a primitive. What is actually very interesting, and it's not something that we can prove with the tools that we have so far, is actually the reverse, because yes, it is obvious that if you take a function and you add a constant, you're not going to change its derivative. But suppose you have two different primitives for the same function. What is the difference between these two functions? Is it possible that there's some other function completely messed up, completely different from big F, that also is such that when you compute its derivative, you get small f? Well, the answer is actually no. If you have two primitive, big F and big G, so suppose you start with two primitive for the same function over the same interval, then there's always a constant, big C, such that big G is big F plus C. So in other words, if you have a function, if you have two primitives, the second one is the first one plus a constant. They only differ by a constant. And this is actually very powerful, because if the question is, hey, can you find all the primitive for one function? Well, if you find one, well, you get all of them. Why? Because simply by adding to that one primitive any possible constant, you're going to be creating a family of functions. And that family of functions is going to be the set of all possible primitives, or the set of all possible antiderivative for that function. So it's very powerful. These two results combined together allows you to say that if you have one, you basically understand the structure of all possible primitives out there. And actually, we can summarize this, the combination of those two ideas, in a definition we call the indefinite integral of a function small f the family of all primitive of that function. The notation for the indefinite integral, because we don't want to compute the indefinite integral. So the notation here is this long s of small f of x dx. So that's the notation we're going to be using for the set of all possible primitive for that function, this long s for f of x dx. The dx just tells us that we are computing the integral for that one variable. Don't worry, in this chapter, every single integral is going to be done with respect to one variable. So if you think about the previous remark, if big F is a primitive for the function f of x, small f of x, then the set of all possible antiderivatives, so the indefinite integral of f of x dx is equal to big F plus c, where c is just any possible real constant. So you need to write the plus c. It needs to be absolutely clear that when you're computing integrals or indefinite integrals, you're going to answer with a family of function and not a unique function. Okay, this is really important. You're really giving as an answer a family of function. The small f, so this is just terminology, is also called the integrand. X is, of course, the variable of integration, and typically the dx tells you what is the variable. So x is the typical variable that we use in these questions. All right, with the work that we did before, let's just do a bunch of examples. Let's find the indefinite integral of 6x squared. Well, we know that 2x cubed is one primitive for 6x squared. So if you just add plus c, you get the full family. So remember, okay, the set of all possible antiderivative is the indefinite integral. So you need to write the plus c. If not, you're going to be punished. Okay, so, all right, for 1 over square root of t, for the next example, we know that 2 square root of t is one primitive for that function. So if I want the full family, plus c, and that's it, that's all. For ln of x, be careful, we're computing antiderivative. So an antiderivative for ln of x is x ln of x minus x. So if I want the full family now, I just need to write plus c. And remember, we're computing antiderivatives, so we're not computing derivative. A common mistake here when we ask for the integral of ln of x or the indefinite integral for ln of x. We see a lot of 1 over x, but make sure you understand that you're going the reversed way. And one thing that should be clear in this section is that we were always given the big F and we only did verification. We did not compute even one primitive. So the idea of getting the full family is not within reach yet. But the next sections, it will be about going and finding these primitives using formulas or techniques of integration. But anyways, for that section of what is a indefinite integral, which is a family of primitive for a function that is obtained simply by having one of them and then just adding a constant to get the full family. That's it. That's all. Bye-bye.